I've been mentioning fission and fusion a lot, so we're going to get into the nitty-gritty details of what fission is and what fusion is, because they could potentially be fantastic sources of energy. So what is nuclear fission? Well, when you undergo fission, that is splitting a larger nuclei into smaller ones, usually one large nuclei being split into two, but it can be different than that. Now, the only elements that undergo fission are uranium-235, uranium-238, and plutonium-239. These are all unstable in a way, and they're very large, that they break into smaller particles. Okay, so if I'm asking you to identify different types of radioactive decay, if it's not starting with uranium-235, uranium-238, or plutonium-239, it's not fission. Okay, so what happens is that heavier nuclei, they might not split in the same way every time, but they do have to add up, right? If I write my transmutation reaction, they do have to add up. But there's actually a wide variety of combinations and examples. So if you look down here, essentially what happens if I got a uranium-235, I hit it with a neutron to actually induce the fission. And uranium-236, super unstable. So it breaks into two smaller, more stable particles. In this case, I have written krypton and barium. It can be multiple other combinations as long as all of my numbers add up, and it also releases neutrons. So all fission reactions produce two medium-sized nuclei. Okay, so in this case, I have krypton and barium as my examples, and several neutrons. In this case, I have 3, it can be 2, it can be 4, but it does also release neutrons. Again, everything still has to add up. Okay. Now, I also wrote over here, I get some gamma rays. So whenever fission happens, yes, we do have a release of gamma radiation. So this is the overall reaction. You have a neutron essentially being bombarded into or hitting a uranium-235, which really makes uranium-236, which completely falls apart. Okay, so uranium-236 does not last very long. And then I end up with, this is one of my possible reaction products, barium-141, krypton-92, and 3 neutrons. Notice these do add up. Okay, everything at the top, this one adds up to, that should be 236. This is upside down. This should be 1 on top, 0 on bottom. Way to go. And then 236 on top. So 141, 92, and 3 1s. Okay, this 3 does play into the masses, adds up to 236. And then 56, 36, and 0 add up to 92. Okay, so they do have to add up. That's a typo. I'm going to fix that. There we go. That's what it should look like. Okay, so other options, right? I said krypton and barium are only one of those possibilities. We can also get strontium and xenon, bromine and lanthanum, or like all of these are possibilities. They all balance out to 236 on top and 92 on bottom. How this kind of works and produces energy, essentially, if I start a reaction with a U-235, I said I bombard it with a neutron, okay? Since each U-235 generates 2 to 3 neutrons in that reaction, those neutrons can hit other uranium nuclei, and there's a possibility of a repeating chain reaction. And that's how we get the energy going. Now, if you think of in a bomb instance, it gets to be uncontrollable. But we have to control it in a method within nuclear reactors, but it's the same type of reaction. So you hit a neutron into your uranium, I get my 2 products and 3 neutrons. Those 3 neutrons hit 3 more uraniums, those break up, so on and so forth, and I get all these different products. Okay, chain reaction means it just kind of like goes by itself. I have products that are reactants of the next reaction. Okay, so how do we control this? We have to know the difference between what is called the critical mass and the supercritical mass. So critical mass is the minimum amount of uranium-235 needed to maintain a chain reaction. So in a nuclear reactor, we need the critical mass. We need to maintain that critical reaction for a constant production of energy. If it fizzles out, we're not going to be able to get it back going. Okay. A supercritical mass is when the critical mass is exceeded, so I have too much uranium-235, and it results in an uncontrollable chain reaction. Okay, that's what happened in Chernobyl. If we end up with a supercritical mass, then everything melts down, it gets out of hand, and you can't like rein it back in, which is a problem. So if we've got to control it in some method. It is a very delicate balance maintaining a nuclear reactor. Now, if you are wanting to do a bomb, then we hit that supercritical mass, everything goes crazy, and that's what you want in that instance. So I'm going to talk about weapons first, and then a little bit more in depth about nuclear reactors. So a U-235 is what we use in nuclear weapons, or what we did use, right, in nuclear weapons. You start with two subcritical masses, so they're not going to undergo chain reactions until they're combined. And then when you combine them, you either produce a critical mass or a supercritical mass, and then it just continues to do that chain reaction and release all of that energy. So the critical mass of uranium-235 is about 1 kilogram. So that's like 1,000 grams. That's not very much. So you just have to keep them separated essentially in the bomb until you want it to go off. Very small amounts produce very large amounts of energy, right? So the problem with this, if we need uranium-235, because that's the mass that we're going to use in the bomb. 238 doesn't work this way. I'm specifically right now talking about U-235. Naturally occurring uranium is only about 0.7% uranium-235. So we have to actually mine it and find a way to get it to be more uranium-235 instead of the other isotope, just 238. So what we do is we separate the uranium-235 from those other isotopes. How do we do that? There's two methods. We can do enrichment or transmutation. So enrichment is taking out those undesired isotopes. It's a very difficult process. This is like a pictorial representation of what goes on in enrichment. And then we can get it to actually use for power and stuff. We need it to be like 4 to 5%. So we do a lot of enrichment to try to get it to use for power. For military use, when I'm trying to do those two critical masses or the subcritical masses, it needs to be like 90%. So that takes a lot of energy and effort. Okay. Transmutation, on the other hand, we can also do. You can use a nuclear transmutation reaction, which is induced by neutrons, right, by us, to convert U-238 to plutonium-238. Now, I haven't talked about plutonium-238 yet, but what we can do, because U-238 is not useful for this fission process that we want, if we hit it with a neutron and get uranium-239, it undergoes beta, and then I end up with plutonium. You might have heard of plutonium before. Plutonium is also one of those fissionable products, but this we can actually use for bombs as well, or for nuclear reactions. So once we get it to that about 3%, we can use it to produce nuclear energy. So what we have in a nuclear reactor are called the fuel rods. That has uranium dioxide. That's where the uranium is. It's encased in either zirconium or stainless steel tubes. Okay, so that's where the energy producing stuff is, the fuel rods, if you will. Okay. Now there's also what are called control rods. So these are the control rods. They are made of cadmium or boron, generally. Those are good at absorbing neutrons. So if you think about the reaction, if I introduce a control rod, it's going to absorb some of those neutrons so that they can't do chain reactions. So they actually control the rate of that reaction. So what happens is we insert however many control rods we need to keep the reaction at a certain level. You take out the control rods, energy increases. You put in the control rods, the reaction slows down and stops. Okay, so the issue with Chernobyl, if you watch the HBO series, which I highly recommend, they had an issue with the control rods and they used cheap materials, and that's what caused all of the problems. But the control rods are extremely important. Okay, so what it does is it produces that energy, and just like what we do with coal or natural gas, we burn it. We don't actually need to burn anything here. It just produces energy. And we use that energy to heat up water. Water, then we use it essentially to, generate electricity. Okay? Turns the steam turbine, generates electricity, and then we put the water back in, it gets hot again, and we use it again, and we use it again, and we use it again. The only difference between this and burning coal or burning natural gas is that the heat is coming from a nuclear reaction. It is not being produced by burning coal or natural gas. So if you've ever been to Clinton, right? Clinton is in Illinois. This power plant, I believe it's still operational. You might have noticed that the lake at Clinton is pretty warm compared to other lakes. And that's because that water is used to absorb that heat or energy in these turbines. Now, that water's not absorbing any radiation, so the lake's not radioactive. It's just warm from absorbing energy. So it's not dangerous, but that is one of the cooling processes, and that water is heated up, turns the turbine, and that's how we get energy. Now, one of the issues, of course, is the products. I was talking about all those radioactive products that uranium-235 produces. We're trying to use thorium-232. It could be a potential fuel source with less nuclear waste, but we have to do a little bit more of induction, and that's still in the process of being studied. So at the end, when we have fuel rods that do not produce energy anymore, so spent fuel rods, what do we do with them? So they are full of those fission products, right? Those two particles that come from those fission reactions. They have to be replaced, or we can repack those fuel rods with more uranium. But what do we do with all of those products? Okay, so the nuclear waste, you might have seen pictures like this before. A lot of the times we will store those spent fuel rods in a substance or in water so that they don't give off too much energy. Some of the things in there, some of the products are like cesium-137 and strontium-90. Those are an environmental hazard. Iodine-131, if you're exposed to iodine-131, like ingestion in that causes thyroid issues. Plutonium is a product also, and it can be weaponized. So we need to be careful with plutonium. So there's a whole bunch of products, and we're like, what are we going to do with them? So one of the suggestions has been to bury them in the bottom of the ocean or in a mountain or something like that, because as long as they're encased and those cases hold, nothing's going to leak out. We're going to be fine. Now, sometimes, of course, there are leaks, which is kind of the issue. So we need to be careful with that. But the amount of any of these that are produced is so minuscule compared to the amount of carbon dioxide that's released in combustion. So again, why nuclear energy is definitely something that we use in the US for about 20% of our power, but could be more beneficial to use more. Personal opinion.